So in this example, we're going to look at what happens when we need to maximize our allocation in Hungarian algorithm problem. So in this context, we've got 4 employees of a company, Alex, Brad, Cassie, and Diana. They're trying to generate some hype around their new product. The matrix below shows how many strong leads they have in each city that will likely result in the uptake of their product. And we're going to determine the optimal allocation to find out where it is best to send each employee to get the most overall sales. So Adelaide, Brisbane, Canberra, or Darwin. Now, first thing that we do when we're doing a maximizing problem is we actually look at our matrix and we're going to effectively invert it. And what I mean by inverting it is that we are going to look at the biggest number in there, which is 11, and we're going to subtract everything else from that 11. So 7 from 11 is going to give us 4. 11 take 4 is going to give us 7, 6, 5, 8, 3, 1, 2, 7, 5, 3, 1, 0, 6, 7, and 8. Okay. Once we get to this step, this one in the pink second column, we're actually just doing the exact same thing as we've done before in our Hungarian algorithm minimizing problems. So we're just going to basically be minimizing this inverse set of numbers, which will give us our optimal maximizing values. So if we look in here, we find our minimum, which is 4. We're going to take that away from everything in that row. We're going to do the same with 1 from that row. Same with that with 1. And then we've got 0 here, so we don't need to do anything. So this gives us 0, 3, 2, 1, 7, 2, 0, 1, 0, 2, 4, 6, and 0, 6, 7, 8. Now we need to look at the columns, and often we don't actually need to do a lot of work to the columns because, as you can see, there's already a 0 in this one, there's already a 0 in the third one and in the fourth one. So we just need to subtract 2 from everything in that column. So if we just write the ones that we already have, which is 0, 7, 6, 0, 2, 0, 2, 7, 1, 1, 0, 8, and then 1, 0, 2, 4. Now, if you just have a quick look at what's happening on our matrix in the bottom left corner, if we were trying to allocate straight away, we can already see that person A and person D are only able to do Adelaide. So that means that we can't come up with a solution. But to confirm that, we use our step 3 of the Hungarian algorithm, which is to cover up the lines with the minimum number, cover up the zeros with the minimum number of horizontal vertical lines to confirm that we have to move on and do something else. So if we look at this column, there's 2 zeros, this row has 2 zeros, and this one has 1 in the row and column. So let's cover those two, this one's left over. So as we can see, we've only got 3 lines, whereas we need 4. We need the same number of lines as the number of rows. So in this case, the thing that we need to do here is to find our minimum number that is not covered, which is 1. We are going to subtract that 1 from everything that is not covered at all. We are going to add that to things that are covered twice. And the values that do not have, the values that are only covered once, so here, here, they stay the same. So first of all, I'm going to draw those ones in that are remaining the same. So 0, 1, 0, 0, 6, 0, 0, and 8. I'm going to draw the ones that have added 1 to them, that have been covered twice. Now I'm going to look at the ones that are fully uncovered, which need to have 1 subtracted from them. And 1, 1, 3, 6. Now if we look at our matrix that's left behind, some of you might already be able to see that there is a potential pattern that we could do here. So what we're going to do though is to still check it with our covering of the zeros. So we've got 2 zeros in that row, 2 in that row, 2 in that column, 2 in that column. So we can attack whichever ones we want to do first. Those two. Now, no matter which way we attack this one, we can't cover both of these remaining zeros with one line. Therefore, we can tell ourselves that we have got a solution here. Now, what we're going to do is we're going to look and see if we can pull that solution out. So we look at the things that can only have one option first. So person D can only go to Adelaide and person C can only go to Darwin. Now, because of the person going to Adelaide, that is knocked out. So they must go here. That's knocked out. So they must go here. Now, if we transcribe that onto our original matrix, we can see that we have an allocation here, which means that our optimal allocation is to send Diana to Adelaide, Alex to Brisbane, Brad to Canberra, and Cassie to Darwin. That's going to result in the most overall sales. And if we look at here, by adding all of these together, we get 11 plus 4, which is 15, plus 10 plus 10 gives us 35 potential sales. And that is our maximum amount.